The next stage of our adventure is industry, which uses over half of the world's energy and electricity. We've learned so far how to get U.S. mobility completely off oil by 2050 at historically reasonable speed, and how the building stock, which uses 3/4 of U.S. electricity, could also become 3 or 4 times more efficient, saving $1.4 trillion net present value with a 33% internal rate of return. Really juicy. Now we'll explore how U.S. industrial efficiency can at least double with at least a 21% internal rate of return, and similarly abroad, and also how to save energy indirectly by saving some of the most energy intensive materials that are produced. Reinnovating Fire's industrial analysis starts with the Energy Information Administration's 2010 forecasts and backs out the projected compositional and efficiency changes and the added cogeneration called CHP, combined heat power. Then we subtract the energy no longer needed to refine the hydrocarbon fuels that transportation no longer needs, but we add back production of biofuels and hydrogen. We count some additional technologies that Berkeley Lab said are entering the market, and then we complete the cost-effective cogeneration and waste heat recovery slate to get 5 quadrillion BTUs, or quads, or roughly exajoules, less industrial energy use in 2050 than in 2010, despite 84% higher industrial output. These efficiencies together save $0.9 trillion net present value at a cost of $0.2 trillion. We also count a range of integrative design savings not already included, but only for dry power and fluid handling systems, not for other process equipment or for any process design. That's a big conservatism, as the next 2 lectures will show. Now, RMI's industrial practice has never achieved industrial savings as small as this analysis assumes. I'd be really disappointed if we did. And yet the US can still virtually eliminate industrial use of coal, oil, and purchased electricity by 2050. This analysis does not count feedstock uses, using molecules rather than burning them. We agree with the national academies that that will be largely, if not wholly, replaced by materials efficiency, loop closing, and biomaterials. Or renewable electricity could be increased to displace some or all of the remaining fuels. At recent renewables prices, this switch should further reduce cost and increase profits. As with buildings, but differing in detail, implementation needs systematic barrier busting, mature delivery by well-trained people, sound allocation of capital, and owners paying attention. None of that's easy, but it has vast rewards. A word of caution about national energy and carbon accounting. National emissions add up more or less to global emissions, but substantial portions are embodied in goods and services that are flowing in international trade. For example, in 2007, Europe was responsible for CO2 emissions roughly 39% greater than showed up on its books, and the rest was embodied in net imports that provided half the primary materials used directly and a third of those made into European products. Increased imports from energy and coal-intensive China may have considerably increased that fraction since then. Embodied energy is important today, but it'll become less so as China cleans up and becomes more energy efficient, as materials are saved, and as some manufacturing is reshored. Now, in the 2010 global Sankey chart, today and in the next 2 lectures, we're going to focus on cleaning up 3 big terms striped in magenta. In the order of which I'll present them, these are industrial process heat, the use of an energy-intensive building materials, and electricity used in industry, since we already discussed its use in buildings and increasingly in transport. You can see that the middle and right-hand magenta bars add up to nearly 3/5 of the total CO2 emissions at the far upper right. And that fraction rises to more than 3/5 when we include the associated methane emissions at the lower right corner. Those, by the way, are old estimates of methane emissions from the oil and gas industries. Those are now known to be much bigger than was thought in 2010, but I didn't try to rejig the whole chart to update that. Now let's overwrite this global Sankey chart with a magenta agenda for transformation, starting again on the right with the emissions. Primary fuels are often first converted to mobility fuels, pipeline gas, electricity, plus it's twice as big waste heat, and the brown stream of feedstocks, mainly for plastics that ultimately end up as CO2, methane, and solid waste. On the supply side, the agenda to save carbon and money has to combine at least 5 main tasks: electrify mobility, competing with green hydrogen and perhaps some advanced biofuels, thereby eliminate oil refineries, decarbonize electricity, shift heat in buildings and industry from gas and coal to very efficiently used electricity or hydrogen or direct renewable heat, redesign processes to need cooler, less or no heat, and redesign activities like structural design and construction methods to save those energy intensive materials. So those are the agenda items shown in magenta. Now, nearly all the global climate and energy conversation is focused on this supply side final energy column, but this course focuses mainly on the cheaper, faster, even more powerful efficiency gains in the equipment and sector columns to get the big multipliers of energy and use efficiency, ETA, in saving upstream supply. Efficient use also points us toward the bottom layers of the chart, where we can redesign agriculture and design out waste, both important for many reasons, and we'll talk about those a bit in the extra section after this class. Now, please focus on the dark red industrial sector, where it says industry towards the left. It uses about half its energy to heat materials and the other half to beat or treat those materials in machines or processes, including adding reactants that get incorporated into the product, like coke, whose carbon helps turn iron into steel. Coal and natural gas provide most of that high temperature process heat today. Please notice also that in the equipment column, the furnaces and boilers item in red shows a magenta product of 2 different savings in energy to make a ton of stuff times the savings in tons of stuff that we need to do the job. Hold that thought. We'll get back to it. Now, this IPCC diagram schematically illustrates where about a quarter of global industrial energy can be profitably saved with current methods, and another roughly 20% with further innovation. These are both widely accepted figures that, as we'll find, are conservatively low. That analysis covers in the circled number 1 at the upper left, conventional efficiency gains like insulating furnaces, cascading recovered heat to other processes, and recycling more materials. Second, fuel switching and carbon capture, since their purpose is climate protection. Number 3A, more efficient use of materials in manufacturing, like reusing old structural steel without remelting it, or reducing yield losses in blanking and stamping sheet metal. Those losses are about half of the aluminum that's produced, a quarter of the steel, a tenth of the paper that currently gets scrapped and recycled within industry itself. So yield losses can contribute more internal recycle if we reduce them. And then 3B, designing products to use materials more efficiently, such as dematerialization or lightweighting or longevity, or all of those. Number 4 is delivering services more efficiently, for example, by car sharing or by higher building occupancy. 5 is reduced service demand, like public transport or better urban design, so we don't need so much transport. And some of these terms are unexpectedly big. For example, 3/4 of the steel in commercial buildings could be saved if safety codes were accurately applied and design life were stretched from 30 to 60 years up to, say, 80 years. The average British car is driven about 4 hours a week by an average of 1.6 people. So its seats are averaging 2/3 empty and it's sitting 98% idle. That's a lot of steel and other stuff just sitting around with at least fourfold saving potential for mobility policy and business models. Now, obviously, the product of all of these terms offers huge potential saving, plus the emitted terms at both ends, both in extraction, an example in our later case studies, and downstream in hedonic efficiency, like whether that next garment or trip really makes you happier. But in this lecture, I'm going to focus on industrial demand. In the next lecture on cross-cutting equipment, that's the solution space most studied and yet most underrated. And in the third of our 3 industrial lectures, we'll focus on redesigning processes. Global industry uses roughly half of all delivered energy, and it causes about 1/3 of greenhouse gas emissions. Of industry's final energy, about 70% makes process heat, and 90% of that is fossil fuel. Thus, nearly 2/3 of industry's final energy use, or 1/3 of the world's final energy use, is fossil fueled process heat. Industry also uses nearly half the world's electricity, but only about 15% of the energy that industry buys is electricity because it's typically too costly to use for process heat. The other 85% of the energy industry buys is fossil fuels that are burned to make nearly all the process heat. And yet, as this graph shows, half the process heat is needed at under 400 Celsius degrees. That's several-fold lower than the combustion temperatures. And nearly 1/3 of the process heat, the 2 green wedges, is needed at under 100 degrees C. So we boil water into steam by burning fuels, not because boiling needs combustion, but because that's what our ancestors did. We make materials like steel and cement in ways that are designed to use combustion temperatures because fossil fuels were handy, so we just burned them. But they burn at upwards of 2000 degrees C. Well, to reduce these mismatches between the temperatures needed and the temperatures supplied, good industrial engineers try hard to provide only the temperatures that each process actually needs and to cascade recovered heat to successively lower temperature uses, but a lot of designers aren't that careful. The key point here is that most process heat does not really need anything close to combustion temperatures. The most energy-intensive industries are cement and steel, accounting for most of the industrial energy growth in this century, and with half the world output now in China. And there's some other big ones too: chemicals, petrochemicals, ammonia, aluminum, and paper. This graph shows not the energy used, but the CO2 released. Only 45% of the global total of industrial emissions comes from process heat. In other words, less than its energy share, which you'll recall is 70%. And that's because much of the process heat comes from natural gas, which is less carbon intensive than coal or oil. Well, that comparison doesn't count methane emissions, not shown here, which can more than offset that advantage. Now, perhaps somebody will develop very simple, cheap, and scalable carbon capture, especially for the concentrated flue gases at big industrial furnaces and boilers, but both as an insurance policy and because it's probably more profitable and very worthwhile for other reasons, decarbonizing global industry must also substitute for fossil fuel process heat. As we'll see, there's a rich menu of demand-side solutions here, even though we'll probably still need considerable process heat for decades. Supply-side substitution often means electrification. Special or very hot processes can, of course, use electricity directly, often delivered as infrared or microwaves, both of which you can tune to drive specific reactions, rather than by brute force resistive heating or electric arcs. Heat is cheap to store, even at high temperatures. That makes variable renewable electricity an attractive source now that it's getting very cheap. But several-fold more efficient than resistive heating would be heat pumps, which can concentrate heat to deliver temperatures up to at least 180 degrees C. Heat pumps can deliver several units of heat per unit of electricity. They can be boosted from lower temperature waste process heat recovered. And of course, they can easily produce the high pressure steam widely used to deliver industrial process heat. So that's a pretty easy conversion. Better still is not to need the heat. Thus, by eliminating natural gas, by choosing up front to install no gas pipe and do no combustion, Tesla's all-electric, all-photovoltaic powered gigafactory making batteries in Nevada saved a precious 6 to 12 months on its state air permit. What's that worth in the battery business? They then displaced the normal 1 megawatt, thermal megawatt of gas boilers for solvent redistillation with a 15 kilowatt electric heat pump, because it turned out the process only needed a 1.5 Kelvin change in temperature. So that physics smart choice saved 98.5% of the energy and all the emissions. And it was very close to Carnot efficiency. A European factory's retrofit similarly saved 92% of the process heat energy. So before you just replace a furnace or boiler with a heat pump, carefully consider how much heat and how hot you really need for that process. Indeed, a big problem with a lot of the statistics, like you saw earlier, about how much process heat we need at what temperature, is they often don't specify whether that's the temperature we supply or that's the temperature that the reaction or desired change of state actually requires. Those two often get mixed up. Now, there are also some important renewable heat opportunities: geothermal at low and medium temperatures, biomass and solar at any required temperature. Optically concentrated direct sunlight can melt or vaporize any material, even on a cloudy day when there are fewer watts per square meter to capture. Solar radiation, whose color temperature can be twice the sunny day, roughly 5,000 Kelvin, can melt metal if it's absorbed by a highly selective surface in a vacuum. Solar thermal technologies are so simple and scalable that they could realistically grow from under 0.002% to upwards of 30% of global process heat needs. That's a $2 trillion market, and reach, say, 5 thermal terawatts, nearly 10 times today's global photovoltaic capacity. This is a logical evolution for the concentrating solar thermal electric technologies that were developed over the past few decades, but have trouble competing with photovoltaics. And it can use their heat storage technologies. It may yield cogeneration, process heat, desalination, and other hybrids with electric generation. And the capital cost for solar process heat should drop into broadly attractive ranges as innovation and scaling expand beyond today's niche markets. We already see the beginning of this. In Bakersfield, California, a consortium including Shell and ExxonMobil planned to start building in 2019 an 850 thermal megawatt solar steam plant to displace natural gas for enhanced oil recovery, gas that was equivalent to about 15% of the oil they were recovering. The elegantly simple solar design blocked wind by enclosing big razor-thin mirrors in greenhouses, keeping them precisely focused with just 1/10 the structural weight because there's no wind load. The greenhouses would be automatically washed each night. The washing fluid was fully recovered. This Bakersfield plant was expected to cost 55% than its predecessor, shown here, which had been built 5 years earlier in Oman, where the next plant was to produce over 2 thermal gigawatts. However, delayed investments unfortunately weakened the maker, a firm called GlassPoint, which then went broke in the pandemic, but it was revived in 2022 with a 1.5 gigawatt thermal solar or Saudi project to produce alumina from bauxite. That'll be the world's largest solar steam plant. And for that to compete in Saudi Arabia is pretty impressive because they have some, but they also have relatively cheap fuels. Now, meanwhile, in December 2021, the Department of Energy launched the HelioCon consortium at the National Renewable Energy Lab, NREL, to cut in half the heliostat mirror field's mirror cost within a decade. And that goal already looks well within reach. And a lot of kinds of solar processes, heat, and its available cheap heat storage need and are starting to get better data, better analysis, easier finance, hybrid and stacked thermal electric systems. So it's getting to be an interesting business. Now, at least two firms, Heliomax and 247 Solar Heat, have proven that they can produce 1,000 degrees C or more solar process heat in sunny climates at attractive costs. Heliomax, whose California demonstration plant is shown here, uses a cleverly simple way to keep its mirror field precisely aligned in real time. The firm recently got well capitalized. It launched a solar cement effort. And meanwhile, 247 Solar Heat has developed a low-cost way to store the heat from its 1,500 sun, roughly 970 degrees C concentrator in fire brick or in ceramic pellets, which can then heat air to similar temperatures 24/7, hence the name of the firm, for process heat. Or they could do power generation in a 400 electric kilowatt Brayton microturbine, or both. And even higher temperatures look feasible. Next, though, we need industrial processes like cement making redesigned to work gracefully with such solar heat sources. But whoa, before we rush to substitute renewable supply for fossil fuel supply, what should we do first? Start with demand. Need less, use other, use less, use longer, use again. Align incentives to do all that. Only after minimizing need should we redesign the process to use less process heat, cooler, and cleaner. So practically everybody's doing this backwards. Take this menu seriously and you will learn how to do almost everything with almost nothing. How big is this prize? Could be the biggest in the whole economy. Let's see why. Wasted materials are extraordinarily pervasive, as this shocking graph of natural capitalism data will reveal. Around 1990, the US economy mobilized a total mass flow of 20 times each person's weight per person per day, excluding about 4 times more in water that was returned clean rather than dirty. And yet only a quarter of that vast mass flow actually went into production. The rest was lost in extraction. Of all the inputs to manufacturing, nearly all also went to waste. Of the products made, 6/7 were consumer ephemerals thrown away after one use or no uses. And of the durable products that were still in use 6 months later, only 2% ultimately got composted or recycled. So of every million grams grown or mined, only about 50 grams per ton got fed back into nature or manufacturing. And that's partly because so much of the waste was toxic. Thus, the mass flow in the US economy was roughly 99.995% waste. Does that sound like a fat business opportunity? Now, an economy delivering the same or better services by applying the 4 principles of natural capitalism would grow more and mine less of the reduced inputs. It would use radical resource efficiency to minimize losses in extraction and manufacturing. By producing durable and dematerialized and long-lasting products, manufacturing would close loops and design out toxicity, so most of the dwindling waste flows can return to create more value, either as technical nutrients feeding industry or as compost feeding nature. A solutions economy business model speeds these shifts by rewarding both providers and customers for doing more and better with less for longer. And some of the increased profit can then be further leveraged by reinvesting it in regenerating nature to help the most scarce and precious forms of capital, nature, and people to flourish once more. So now let's dig further into how to use these and similar demand side methods to decarbonize most industrial process heat. The Energy Transitions Commission found in 2018 that the supposedly harder to abate sectors, heavy transport and industrial process heat, could be completely decarbonized by mid-century at a cost below 0.5% of the 2050 world GDP. Their analysis was convincing and helpful, but it looked to me quite conservative. Sure enough, the Commission's chairman announced in late 2020 that the UK could cut its total greenhouse gas emissions not by 80%, but by 100%. Instead of costing 1 or 2%, it would cost 0.5% of GDP in 2050 because of new developments in just 2 years. But as I dug even deeper into the assumptions about saving energy-intensive materials, I came to suspect that the cost of abatement had fallen not just from modest to more modest, but to negative. That is, it had turned from cost to profit. So in summer 2021, my RMI technical report and MIT Sloan Management Review companion paper, both in your readings, showed how decarbonizing these supposedly harder to abate sectors, heavy transport and process heat, is not particularly hard. It's just differently hard, and it's more likely profitable than costly. As usual, enlarging the system boundary, as Eisenhower advised, makes this problem soluble. Now, the Commission's analysts had proposed some circular economy ways to save materials. Then they emphasized new processes, often with better chemistries that need less or lower temperature heat and release less CO2. They proposed more efficient processes and equipment. They proposed cleaner fuels or renewables. So I've summarized these under productive use and then cleaner process, make better, and make cleanly. All these options are important, but this conventional menu understates or omits 8 prior classes of powerful demand-side opportunities, which I will now illustrate by expanding the system boundary. Let's do that mainly for cement and steel, because those are the 2 biggies. First, we can change how we deliver the services that now need energy-intensive materials. Of 5 obvious examples, at least 3 seem obvious candidates for saving concrete and steel through solutions economy business models. Microreactors can save 80 or 90% of many fine chemical plants' capacity and energy. Shared and connected mobility saves roads and parking. You may recall we learned last week that designing cities around people, not cars, feet, not tires, can save 1/3 of the concrete and 2/3 of the driving. Just like mobility as a service, the solutions economy business model in Chapter 7 of our 1999 book, Natural Capitalism, can lease structural performance rather than selling tons of cement. So the provider and customer will both make more money by using fewer tons. The provider could also reward structural engineers for delivering the best performance with the least material. When I suggested this to the head of a giant cement company a decade ago, he said, good idea. I have several hundred people working on that right now. Well, lacking further news, I later published the concept in your MIT Sloan Management Review reading to encourage competition. Now, this model is taking hold in building services like lighting. It's already won in much of the chemical industry. Dow and Safety-Kleen will lease you a dissolving service rather than selling you a solvent. Mining may be next, leasing conductance services rather than selling tons of copper. The head of the world's biggest gold mining company has already proposed such a model for gold. The World Economic Forum published an article on how this servitization or outcome as a service model is delivering agricultural refrigeration in Nigeria and has enlisted over 50 firms in a global alliance to deliver space cooling services, much like the way the chauffagistes have long delivered space heating services in French cities, the service of chauffage. A solutions economy business model would nicely exploit a juicy new resource, namely that most of our cement and steel are now wasted by inefficient structural design. Improving design, I found, could save roughly half those materials, as explored in your readings. Substituting, for example, tension for compression structures typically gives better strength, aesthetics, and cost with only 1/8 tons. Pouring concrete, which is after all a slurry, into curving fabric forms rather than rigid prismatic forms permits optimal shapes like this beam that can save over half the concrete in pretty common shapes, beams, sheets, and so on. Here's a folded 4 or 5 centimeter thick concrete roof or floor viewed from above, replacing a costlier 30 centimeter thick steel and concrete slab, as we'll see in a minute. Dutch 3D printing of an airy bridge can eliminate most of the massive concrete structure that mostly supports itself, not its payload. And this 2150 square meter pavilion built with hand tools by Colombian peasant artisans illustrates how materials like bamboo and wood can save weight as well as carbon. Now here's a detail of that trapezoidally folded roof slab, redesigned as a floor slab with live loads taken from the German building code. Now the top section drawing on the upper left shows the standard 30 centimeter thick slab spanning 8.1 meters. The middle drawing shows a 20 centimeter thick steel pre-stressed version that uses 41% material. It's got a bunch of holes in it where you don't need the strength. And then the bottom drawing is the section of that folded 5 centimeter thick version, pre-stressed with carbon fiber rather than steel, so there's nothing to rust, and that saves 76% of the material. It is also the cheapest of the 3 options. You might wonder, why is it important to redesign floor slabs? We don't normally think about them, we just walk on them. Well, because they're about half the total weight of a typical mid or high-rise building. These thick slabs need even more concrete than in beams and columns and foundations to support their weight. Well, flat slabs are easily poured into simple formwork, but they make no sense structurally. Look at the little drawings at the far upper left. When you load weight onto a flat slab, it sags so that the top surface compresses and the bottom surface stretches. But concrete strength is far greater in compression than in tension. So most of that thickness provides little strength, and over half the concrete gets cracked. Well, look how much thinner a curved vault or shell can be, resisting load by compression with less stress, minimal cracking, greatly improved material efficiency. The Catalan and Nubian builders figured this out a long time ago. In fact, in 1762, the 6-story Versailles Library spanned up to 7.5 meters with light, shallow, singly curved tile vaults, and it still stands because it couldn't burn. And now some British designers are using 3D printed shallow domes built up to a flat top by thin stiffening ribs, and they're using fabric formed thin vaulted shells topped with concrete foam. That eliminates 62% of the weight and 64% of the embodied energy. You can also save another roughly 15% of core structural materials, 9% of the glazing, 77% of the energy, much time and cost in a mid or high-rise building, like the Singapore one on the upper right, while increasing net rentable space per unit footprint and height by a stunning 55%. How do you do that? Well, it's a Swiss concept called 3 for 2. And the concept designs out a vertical meter odd of mechanical plenum at each story, as you see at the far left. So you can fit 3 stories with a normal 2.8 meter ceiling height. You can fit that into the vertical space normally needed for 2 stories. The mechanical systems are designed out, or they're integrated into other building elements like the facade or the interior surfaces. Cost, complexity, and time fall dramatically. Everything gets better. So now that we know this, why would we build any other way? But as usual, elegantly frugal structural design could go even further. Imitating nature's curvy architectures can amaze, like this armadillo vault, hand assembled with no mortar or glue. Its 399 digitally milled limestone tiles simply sit on each other, held in balanced compression by gravity. These tiles are as thin as 5 centimeters, but they span 15 meters, a ratio of 300. Wow. What if we got as good at vaults and arches as the Amiens cathedral stonemasters were in the 13th century, carving this airy structure that could contain the Cathedral of Notre Dame twice over? In the modern age, only Gaudi's soaring stone forest comes close. And couldn't we do such things with concrete too? Oh, actually, yes. In fact, the world's largest unreinforced concrete dome still stands in Rome. It's called the Pantheon. It's been there nearly 2,000 years. Today, about 60% of the world's cement is made in China, where concrete buildings last an average of about 30 years. Such short life and inefficient design make them need far too much cement. Why aren't we as smart as the Romans? Now, we can also substitute low or even negative carbon materials like wood and bamboo for steel and concrete. Cheap smoked bamboo structures from Simon Velez or Gunter Pauli can be safe from insect damage for 500 years. Or Pliny Fisk's rammed earth, or the ancients' adobe and caliche, or Hassan Fathi's in situ fired ceramic buildings. Build a ceramic dome, build a fire inside, fire it, take out the ashes and stuff and live in it. The cheap husk of the Indonesian sugar palm has lignin fibers with a tensile strength rivaling stainless steel, but 1/7 its density. Modern materials are powerful too. Oh, by the way, I grow sugar palms in the jungle behind me. So modern materials are also powerful. A thin sheet of carbon fiber composite can save 2/3 of the wood in the glulam beam, or 30 to 50% of the concrete in a structural panel. In this photo, the Technical University of Berlin's engineering faculty is standing on a 13-meter span supported solely by carbon fiber ribbons 1 millimeter thick. Carbon fiber anti-corrosion wraps save the 30 or 40% of concrete that you don't need for static strength, but just to cover up the steel rebar so it doesn't rust. And of course, you get rid of the steel rebar with carbon concrete composites. And then the otter-resistant shell of the abalone is tougher than our best missile nose cone ceramics, but instead of being made in an incandescent furnace, it self-assembles in seawater at 4 degrees C. You know, the late Ernie Robertson in Winnipeg listed 3 ways to make limestone into a structural material. You can cut it into blocks as the ancient Greeks and Romans did. That's durable, beautiful, tedious. Or you can calcine the limestone at about 1250 degrees C into Portland cement. That's inelegant. Or you can grind it up and feed it to chickens, and hours later it reemerges as eggshell, which is lighter and stronger than the best Portland cement. So if we were as smart as chickens, we might master this ambient temperature technology through biomimicry. Innovation inspired by nature. We can also combine better materials with smarter engineering. New York's Freedom Tower saved 40% of its cement through stronger concrete and mass decompounding. And now ultra high performance concrete can be more than twice that strong, about 10 times as strong as house concrete. Twisting the 128-story Shanghai Tower, the tallest in China, and the world's second tallest building, cut its wind loads 24% and its structural materials cost by $58 million. Here's another example of elegant structural engineering I heard about. Consultants on the Golden Gate Bridge seismic retrofit first advised massive and costly additions of reinforcing materials. And then an Indian engineer reportedly pointed out that this would worsen the risk because it would slow down the bridge's mechanical period into a frequency range resonant with earthquakes. So small light fixes could simply shift the structure's resonances out of the seismically relevant frequency range. Imagine China makes over half the world's cement. Well, China's once ubiquitous and very energy inefficient shaft kilns, which you can still buy new on Alibaba, produce cement of such irregular quality that the quantity had to be tripled to ensure enough compressional strength. The cement looked cheap per ton, but it was 3 times costlier per durable building. Switching to modern cement making with uniform quality therefore tripled the energy and cost savings, and thus reinventing fire China found that making cement and steel rebar to uniform European quality can make buildings last longer and can thus cut Chinese cement demand 6 to 10%, Chinese steel demand 6 or 8%, global rebar demand 13%, plus similar benefits in consumer goods. Better materials also have important indirect or knock-on benefits. Their lower quantity combines with lower manufacturing energy and decarbonized supply to save more coal. Transporting less cement and steel and coal frees up rail capacity. That can help shift freight from road to rail. China still moves a lot of coal in big trucks. And this shift reduces road damage. It saves cement and money to rebuild roads. Less cement means less transport need and so on, while freeing more rail capacity reduces rail build out and repair, saving more steel and money. So these kinds of virtuous circles can add extra benefit. And as we shift from ephemeral to durable structures, remember the construction and demolition waste is the world's largest non-agricultural waste stream, totaling about a half ton per European per year. And yet it's especially suited to recycling. There's a Dutch technique for smart crushing with just 1/10 the normal force that can selectively liberate they say about 40% unhydrated cement for valuable reuse in new concrete. And the developer claims that globally, this could save about 2.5 gigatons of CO2 per year. These and many other diverse demand side options for using less cement, steel, aluminum, paper, plastics, and so on, multiply to very large savings before we get to circular economy, more benign products, more efficient processes, fuel switching, and renewables. So such efficient end use has big multipliers back upstream to materials extraction and production, leaving a lot less high temperature process heat to decarbonize. So what I've done here in the brighter type at the top is to add those missing first 8 lines to the conventional 12-line opportunity space you saw earlier. In other words, we've greatly expanded the system boundary and made the problem a lot easier. I should also mention one potential paradox in cement. Ordinarily, we want to use a lot less cement and make it with less and cooler and cleaner process heat. But Solidia had a Turkish chief scientist who discovered a carboxylate chemistry that could make cement into a large net sink of carbon, for carbon. In other words, he could save potentially up to 5 or even 8+ net gigatons CO2 per year. And so far, that appeared to have the same or better properties and probably lower cost compared to normal Portland cement. So if that innovation succeeds, probably elsewhere, since he and his CEO both departed, we may want to consider saving cement more slowly to take more carbon out of the air. That would be a nice problem to have. We're not there yet. The carboxylate chemistry stays in the lab, but maybe somebody will rescue it. Now, after that little excursion into saving materials, let's return to first principles. Industry turns raw materials into artifacts whose use delivers services. So as usual, let's start with the demand side, because the first design question is always, why do we want to do this thing? Well, Ono Sensei, the irascible genius who invented the Toyota production system, classified many kinds of Muda, any measurable input that creates no customer value. For example, making defective or unwanted product, anything that doesn't meet customers' needs, making things customers haven't requested and bought, like inventory, mistakes requiring rectification, any unnecessary input or process step, inspection to ensure quality that should have been built in, counting parts. There's a lovely story about when Ford got involved in Mazda. A Ford and Mazda engineer were talking, and the Mazda engineer said, I'm kind of puzzled. You seem to have a lot of people counting parts. And the Ford engineer said, well, how many people do you have at your comparable size factory counting parts in inventory? Mazda's guy thought and said, well, maybe a half a person, something like that. And the Ford engineer said, how do you do that? And the Mazda engineer said, well, here at Mazda, we're kind of simple-minded. Every car that we ship out has two headlights and they both work. So we count the number of cars we ship, multiply by 2, and we bill our headlight supplier for that many headlights. If they happen to have sent us any that didn't work, we're not going to pay for them anyway. So why should we waste time swapping paperwork about the ones that didn't work? We'll just pay for the ones that did work. Another kind of Muda would be repeatedly heating and cooling something to no purpose. You see a lot of that in steel mills. Extra steps to produce something more or other than the customer asked for. Waiting for stuff to happen. Nobody ought to act until the downstream client asks for it. Nobody should be standing around waiting for something to happen. Moving people or goods without purpose is Muda. I once came into a factory making giant chillers the size of a small house. They would bring the sort of carcass of the chiller in with a big crane, and it would sit there while they bolted some stuff onto it. Then they'd move it to another place and bolt other stuff onto it and so on. And by the time it got out the other end of the building, it was all assembled, ready to ship. And I asked the engineer showing me around why they were doing it that way. Why don't you just leave it in one place and bring all the small stuff to it? Move it in once, move it out once. He said, funny you should ask that. One of Odo Sensei's students was here the other day, standing where you're standing. And he looked around and said, no cranes. And of course, if you're trying to get rid of Muda, which literally means no purpose, don't just benchmark against your competitors or against best practice. The right goal for Muda is 0. Get rid of it. And Muda is actually one of 3 cardinal sins in or against lean production, which applies not just to manufacturing, but to every activity. The other 2 are called Mura and Muri. And Mura is unevenness, fluctuating pace, and that's Mura, rather. And Muri is overload or overburden, which often results from unevenness. Now, there's a lean lexicon offering a simple example showing how Muda, Mura, and Muri are often related, so eliminating one also eliminates the others. And the example shown in the diagram is, suppose a firm has to transport 6 tons of material to its customer, is considering options for doing that. One way is to pile all 6 tons on one truck and make a single trip. That would be Muri, because you're overburdening the truck, which is only rated for 3 tons. It's probably going to break. And that also leads to Muda and Mura. Well, second option would be to make 2 trips, say one with 4 tons, the other with 2 tons. This would be Mura, because the unevenness of materials arriving at the customer creates jam-ups on the receiving dock, followed by too little work. This option also would create Muri, because on one trip the truck is still overburdened, and it would create Muda, because the uneven pace of work would cause the waste of waiting by the customer's receiving employees. So a third option would be to load 2 tons on the truck and make 3 trips. This would be Muda, even if not Mura and Muri, because the truck would be only partly loaded on each trip. The only way to eliminate Muda, Mura, and Muri is to load the truck with 3 tons, its rated capacity, and make 2 trips. Simple example, I hope it sticks with you. Because importantly, in production systems, as in daily life, these sins are intimately linked. That Mura creates Muri that undercuts previous efforts to eliminate Muda. There's a lot more to that. If you really want to dig into it, it will serve you well. Now, Jim Womack is a lean production wizard spun off from MIT, and he co-authored with Dan Jones a Welsh professor, a great book called Lean Thinking. And lean thinking in their book means the continuous flow of value as defined by the customer at the pull of the customer in search of perfection, which is zero, Muda, Muda, Muri. All four parts of this definition are essential because lean production to make unwanted goods flow even faster is only making Muda. So contrary to what many business schools teach, maximizing capacity utilization is usually a mistake. More on that in Natural Capitalism, Chapter 7. Specialized, large-scale, high-speed, highly efficient production departments and equipment cause uncompetitiveness. Here's a little example from Pratt & Whitney, the great turbine makers. It's what in the trade we call a monument. They had 12 8-axis, 2,000 parameter automated German grinding machines, $80 million. And they cut the time to grind a turbine blade from 75 minutes to 3 minutes. Pratt replaced them with 8 World War II style 3-axis grinders. It cost 3/4 less. They needed no more total people. They cut the total process time 200-fold from 10 days to 75 minutes by eliminating 9.95 days of difficult and nasty supporting processes. Like they had to embed the workpiece in a special alloy to withstand the excessive forces of the powerful tool. Then they had to dissolve away the alloy afterwards with nasty acids. The process also got vastly more flexible. The big machines you see had been so fast that they slowed down the process too much. They were so automated that they needed too many workers, called support technicians. With high-wage workers, half the total cost, a third the tooling cost, 1% of the production and changeover time, Pratt got a 1-year payback without any salvage value on the monuments that they somehow got rid of. I don't know what they did with them. They missed something, at least at that time. How about casting your blade blanks to near net shape? Then you don't need to grind them so much. How well does lean thinking work? Well, Womack and Jones declared from their early but deep field experience, this is a quote, approximately 50 diverse worldwide manufacturing companies that have tried this approach have typically found that using the same workers and the same capital over a period of 5 to 10 years, production increases by 2 to 4-fold, while inventories, delays, defects, errors, accidents, scrap, and other unwanted outcomes fall by about 4 to 10-fold. And they said a lot of the improvements immediate and dramatic. Quote, if you can't quickly take throughput times down by half in product development, 75% in order processing, and 90% in physical production, you're doing something wrong, close quote. So lean thinking is another important way to eliminate a lot of industrial production and its energy use up front while delivering better service. But lean thinking doesn't just eliminate small wastes. It also eliminates waste too big to see unless we remove the blinders of habit and start to see clearly through the lens of beginner's mind. Here's a sweet example. There was a new environmental manager at Safeway asked to figure out what to do with the fatty waste left from using hot water under high pressure full of nasty chemicals to clean out pipes in their ice cream factory after they made one flavor so they could set up for the next batch of a different flavor. The cleaning and the waste disposal were very expensive. One day the manager asked, why are we throwing out all this tasty, costly stuff? Why don't we just run the differently flavored batches continuously back to back, keep track of the mix zone where the flavors are mixing, and then package and sell that mix zone as, magical mystery tour ice cream, exotic mixed flavors, no two alike, you'll love the exciting variety. Well, it was a huge hit. The profit margin was enhanced by saved raw materials like cream and flavorings, avoided cost for the waste disposal and time and materials for cleanouts they didn't really need for hygiene, the extra production achieved for free by converting cleaning capacity and time into more production, and most fun, the extra profit margin when they discovered that instead of having to discount this non-standard product, they could actually charge a novelty premium for it. Of course, the new product cannibalized sales of old products, but you hope those products were sold by competitors who didn't think of this first. Yum. Well, this delicious example illustrates the logo in the lower right corner, which says Muda Nashi, no Muda. It systematically turns every kind of waste into value and profit, just by asking a different question. Now, industry extracts and processes materials, but as we saw, about 99.99 something percent of the waste mass flow is wasted. Much of this waste will ultimately get designed out or turned into profit by dematerialization, virtualization, product longevity, closed loops, industrial ecology, additive and desktop manufacturing, precision chemistry, and so on. But integrative design keeps getting bigger and cheaper, tunneling deeper through cost barriers. And then come two further design revolutions, biomimicry, which we'll visit in the next lecture, and what Eric Drexler originally meant by the term nanotechnology, that is self-assembling micromolecular machines, which of course nature does every moment, as in our own bodies. Well, put all these layers of innovation together, and most of the world's industrial energy can keep being progressively saved for a very long time to come. The initial design requirements we're learning in this course are just the first step in an almost infinitely long and worthwhile journey to radical efficiency. So to summarize so far, eliminating inefficiency needs lean thinking, no Muda and no Muda or Muri either, no rules of thumb, no infectious repetitus, which is copying this previous set of drawings, and no incrementalism. It also requires us to optimize whole systems for multiple benefits, not isolated components for single benefits. We need to bust barriers and reward what we want. We're going to need faith, hope, and clarity, and the greatest of these is clarity. We'll need a lot of hard work because this unprecedented cornucopia is the manual model. You actually have to go turn the crank. And we need works, not just grace. As St. Francis of Assisi said, preach the gospel at all times. If necessary, use words. Let's consider a few examples to consolidate these design and business model concepts. Your readings included a Harvard Business Review article summarizing our 99 book with Paul Hawken, Natural Capitalism, but I hope you'll read the whole book because integrative design animates just one of its four interlocking principles for doing business as if nature and people were properly valued, but without having to know or signal their value. And that's an even bigger and more powerful set of ideas than integrative design, and it remains ripe with promise that's starting to be realized all across the world of business. Here's a little example of, well, it's a bit more than loop closing. The Belgian entrepreneur Gunter Pauli, who founded Ecover, illustrates his natural capitalist practice with this example from a Namibian brewery. Initially, they were using water to grow grain to make beer. The spent grain got landfilled or fed to livestock whose manure emitted methane. The wastewater got wasted. But after redesign by ZERI, Zero Emissions Research Initiative, Gunter's, Zero Energy Research and Initiatives, Gunter's outfit, the same inputs then produced far more value, but produced no waste because each organism's waste became another's food. That's why there are 5 or 6 kingdoms of life, enough diversity that everything gets recycled. So notice starting towards the top, the spent grain makes beer bread and of course beer out of the original grain. And then the spent grain doesn't just make beer bread, it also feeds earthworms from which very valuable enzymes are stripped out and the rest fed to chickens to make eggs and meat, which I guess we should have added to the drawing. The spent grain is also feeding valuable mushrooms, shiitake, ganoderma. Their protein-rich substrate feeds livestock, whose manure plus the grain-growing wastewater is then digested into biogas, which provides surplus electricity and heat for the mushrooms if you need it. Then the supernatant grows algae to feed fish. The fish runoff and digester sludge fertilize the garden. So starting with exactly the same grain, the brewery that used to make only beer can also now sell 11 other products: bread, enzymes, chicken, eggs, mushrooms, pork, beef, algae, fish, fruits, and vegetables. Every loop has been closed. All waste has become food, just as in nature, creating immensely more value. But RMI was helping redesign a private firm that is the world's largest grower of apples and maker of cider. Our three most memorable findings were first that the apple seed coat being discarded with the rest of the apple core contained powerful antioxidants that were worth more than all the rest of the apple. Nature is really good at protecting seeds. Secondly, the orchard trimmings that the firm was paying to dispose of would make a wonderful substrate for growing those valuable mushrooms that were worth more than the cider. And third, the whole value chain had been spoiled by using the wrong metric. Well, that was discovered by the modern languages graduate who married the chairman's daughter and could have ridden his own ticket, but he chose to start as a manual laborer in the orchards for 2 years. So he was the only executive who actually understood the firm's production process end to end. The other executives were trained in marketing and finance, but they didn't like getting their hands dirty, let alone blistered. And what he found was a metric error so simple nobody noticed, and yet so powerful that fixing it redesigned the whole enterprise. You see, making cider takes sugar, tannin, and flavorings. Apple trees naturally like to grow tall, concentrating these products in smaller apples that are high up because it takes osmotic energy to lift the water. But the orchardists were being paid by the ton. So they trimmed the trees to bush out low so they could be easily harvested like almonds with giant shakers. And this yielded more tons of big watery apples, cheaper to harvest, but then the extra water had to be boiled away to get the desired products. And a lot of apples fell on the ground when you shook the tree. They got bruised, they got dirty, more tons of mush and mud, adding wild yeast strains that spoiled the carefully controlled fermentation. So the firm began paying not for tons of what, but for the ingredients that the process required, and then turning the various wastes into value. And the results were really juicy. Another simple example of natural capitalism in action was how burning the rice straw after the rice harvest in Central California was polluting the air and potentially causing silicosis downwind. So some growers started instead to harvest the straw for straw bale construction, as its high silica content discouraged insects. And then they would flood the fields to rot the stubble and invite in millions of wildfowl to feed and overwinter. Their manure fed the soil and the new wetland ecosystem full of innumerable little critters, crustaceans, and so on. The farmers got new winter revenue from hunting rights, groundwater recharge, and other benefits. The winter wetland area tripled, ducks doubled, geese and swans flourished, birds rejoiced, and straw burning is now but a fading memory. And now the Nigiri project in the Sacramento Valley's Yolo bypass is using the flooded rice fields to feed baby Chinook salmon returning to the Pacific in the winter, creating what they call floodplain fatties, which you will find described at caltrout.org. As the rice farmer John Brennan says, if you're in the rice industry, you're in the water industry. And if you're in the water industry, you're in the fish industry. There's a great New York Times article on this, 18 May 2022, called Why Salmon and Rice Go So Well Together. There's a small but spectacular example of loop closing that we found at the University of Zurich, not ETH, but the other one. The elementary chemistry lab course each year was turning $8,000 worth of pure simple reagents into toxic waste that cost twice that much to dispose of. Well, two of the professors redesigned the course to turn that once through linear thinking into closed loops. The students would simply re-separate the toxic waste they just made back into the pure simple reagents they'd started with, teaching cycle thinking and saving money at both ends. The waste fell 99%, net annual costs dropped by $20,000 or $130 per student, and those students were in strong demand to go help reform the chemical industry. A more elaborate example comes from designer Bill McDonough. Had a project for Steelcase called Design Text. Bill found that the edge trimmings of textiles used to upholster office furniture were considered by the Swiss government to be a toxic waste. What about the edges, or what about the middle of the fabric that you're sitting on? So Bill and his German green chemist colleague, Dr. Michael Braunhardt, screened 8,000 textile chemicals, and they found that, according to their model, only 38 treatments based on just 8 basic ingredients were actually benign, would not cause cancer, birth defects, and so on. But from those 38 safe chemicals, a whole line of fabrics that was more beautiful and durable could be created, and it turned out to cost 20% less. And when the Swiss inspectors came to the factory, they thought their measuring equipment must be broken because the water going out of the factory was a little cleaner than the Swiss drinking water going in. That turned out to be correct. The cloth was acting as a bit of a filter. And the design concept, says Bill, took the filters out of the pipes and put them where they belong in the designers' heads. And he points out when you're done with the cloth, you can compost it or eat it. The late Ray Anderson, the radically visionary Georgia engineer who founded carpet industry leader Interface, found that millions of tons of carpet every year, made largely from oil, get used once, and then after some years when they get soiled or worn, you close your office, move out all your furniture and people, roll up the old carpet, send it to landfill for 10 or 20,000 years since they're making methane, install a new carpet made of more oil, unroll it, glue it down, move back in, and resume operations, maybe sickened by fumes from the carpet glue. Not a good use of oil or land or money or people. Well, first of all, Ray drove Interface to impressive efficiency gains, aiming not for incremental improvements, but for zero waste. And later, they redefined all fossil fuel inputs as waste to be ruthlessly driven out by design. By 2019, this billion-dollar company's total production relied on 89% renewable energy worldwide, 99% in the US and EU, 100% globally for electricity alone. Their water use intensity was down 89% from 1996. Their energy intensity down 46%. Manufacturing greenhouse gas intensity 96%. Waste to landfill 92%. And Interface was sourcing 60% of its raw materials for carpet from recycled or bio-based resources. And now that Ray's original mission, zero greenhouse gas emissions, zero net water use, a fully closed materials loop, reached its 26-year goals in 2020, the firm's next stage of the long climb up what he called Mount Sustainability is to become carbon negative by 2040 and achieve climate takeback, which they defined by 4 phrases. We will bring carbon home and reverse climate change. We will create supply chains that benefit all life. We will make factories that are like forests. We will transform dispersed materials into products and goodness. Ray's next goal was closed loop production. So his team developed a climate neutral, non-toxic, chlorine-free product, so no PVC, that was washable, stain and mold free, beautiful, uniquely nice to use, 4 times as durable as old carpet, used 35% less material, and could be completely remade into identical product with no downcycling. They did later discover one very specific durability problem that kept this particular product off the market, but if and when that's solved, the concept will remain sound. The next step came from this carpet companies asking a different question, namely, who wants carpet? Do you really want to own a bunch of cloth on the floor? Or do you just want to walk on it and look at it? And if that's what you want, why should I sell you a carpet? Why not instead lease you a floor covering service? You see, in the leasing system, the little elves come in the night about once a month, and they replace or lift out and wash with a garden hose and dry and immediately reinstall the 10 or 20% of the carpet tiles that show 80 or 90% of the wear. And those carpet tiles can easily be swapped thanks to the glue-free biomimetic tactiles, little plastic film discs that hold down their corners with nano hairs inspired by gecko foot technology. The 4/5 of the tiles that are under the furniture are fine. They aren't worn because nobody walks there, so you don't need to move your furniture out. The carpet always looks fresh. Any tiles taken away are remade into new ones. The customer's operations aren't disrupted. Interface captures the durability value. Well, a decade later, the U.S. Internal Revenue Service had agreed on details of the tax-deductible net operating lease that makes the financial model so profitable, although customers remain slow to adjust to carpets being an operating rather than a capital cost. But meanwhile, perfected remanufacturing had cut the net flow of materials and the energy needed to make and move them by 97% without remanufacturing, or 99.9%, 1,000-fold with remanufacturing. The capital needs fall by 90%. The customer needs to put up no capital. More jobs are added delivering the service that are lost at the factory by making less carpet. So if you're in the old carpet business, it's pretty hard to compete with this model. So this is the heart of the solutions economy business model. Both parties make money in exactly the same way, by doing more and better with less for longer. And that alignment of interests is more important than the detailed form of the transaction, sale or lease or whatever. Ray Anderson's next ambition was to make the carpet entirely from corn wastes grown organically by rural ex-sharecroppers in ways that enrich soil, decarbonize the air, and restore equity in rural culture. In due course, I expect that'll happen too. Another step in Ray's expansive vision of business that takes nothing, wastes nothing, does no harm, and does very well by doing good at the expense, not of the earth, but of less alert competitors. That approach keeps spreading, and now Interface is buying discarded nylon fishing nets from poor coastal communities in the Philippines and Cameroon, and thus protecting marine life while supporting 1,500 families. Removing any contradiction between what you do at work and what you want for your kids when you go home makes natural capitalist firms the most exciting places to work, so they can attract and retain and motivate the best talent, and their people become unstoppable. And you're doing very well, as this scorecard shows, for just the first 4 years of the journey Ray Anderson chronicled in his important books, Mid-Course Correction and Confessions of a Radical Industrialist. As Ray so beautifully showed, natural capitalist firms take their values from their customers, their designs from nature, and their discipline from the marketplace. Such businesses don't need conventional environmental regulation. They're way ahead of it. And for them, it becomes kind of a quaint anachronism, because the firms that need it will probably already be out of business or heading that way because they spent too much money and time making things nobody wants. Things that in the 20th century we used to call waste and pollution, but now we know to call them unsaleable production, because that term makes us focus on why we're paying to make stuff we can't sell. Let's stop making it. Let's design it out. The world is awash in plumes of waste and pollution heading downwind, downstream, down through time, and the costs and benefits often go to different people. There's a new National Academy proceedings paper that found that for US PM 2.5 air pollution, white people experience about 17% less exposure than their activities generate. Black people, 56% more than their activities generate. Hispanic people, 63% more, creating serious pollution inequity. And what Hank Patton calls temporal plumes going downstream in time also harm future generations who suffer from a disability he calls temporal dislocation. That is, they're not here yet or they can't vote yet. Hence the children's school strike for climate movement. And Hank has actually figured out a transactional framework for future generations to buy what they want in today's market. It's called intergenerational commerce. But waste and pollution exposure to all beings at all times can be reduced or eliminated by properly designing our cybernetics, our feedbacks. I once met the world's first environment minister in Australia, who had cleaned up rivers by making factories put their water intake downstream of their waste outfall. Simple feedback. How clean would you make your car if its exhaust pipe, instead of being aimed at pedestrians, were plumb back into the passenger compartment. How safe would you make the chemical plant you manage if you and your family had to live at the downwind site boundary? A good idea that Shell almost adopted. Admiral Rickover, the father of the U.S. nuclear Navy, wanted to ensure that his nuclear submarines would have top quality hull welds. So he simply told the welders and their CEO that they would all be aboard for the maiden dive. Such simple cybernetics can remind us to design as if our life depended on it, because it does. So that's a very short dip into natural capitalism. I hope you'll read it. So to review, in industry, as in buildings and mobility, our design process goes in the opposite direction to the flow of the resource throughput. It always starts with why, with purpose, with intent, with the end use service the customer wants. Then it works back upstream toward the resource inputs to leverage ever bigger savings. More on that big and important concept in the next lecture, but first I'd like to address the process and tools of innovation as I end for today. How many of you worked in industry? Well, you know, and the rest of you may have a chance to discover that large organizations work in rather strange ways. We've all lately been taught or retaught a simple linear mechanistic view of how to make systems better. You want to do something, you plan how to do it, you take action to do it, and then you figure out how does the result differ from what you wanted, and you have a little correction loop. But innovation is actually a whole lot more disorderly than that. It looks more like this. Charrettes are the best way we know to capture that yeasty creativity and bake it into clear, practical, valuable innovation. The name charrette, literally a little cart, is from design concepts that used to be held in Paris in the Palais des Beaux-Arts period. They had horse-drawn carriages trundling through the cobbled streets of Paris, carrying architectural models to the place of judging. But on each cart gathered around the model, there was an excited gaggle of architects furiously debating and putting the finishing touches on their physical model. So architects came to use the term charrette to refer to a very intensive, interactive, transdisciplinary design workshop with a short deadline and an ambitious deliverable, doing weeks or months of work in a few days. Charrettes often alternate between plenary and working group sessions, ideally in a room designed like RMI's Innovation Center studio with adjacent breakout rooms. So we cross-pollinate and mix and stir and move people around so all the systems and ideas get hooked up. We've used Charrettes to redesign hundreds of buildings, everything from cars and ships to refugee camps and mines, many heavy industrial facilities, a house for language-enriched great apes with the apes on the design team, whole enterprises. Our most complex charrette, the 1993 greening of the White House with Department of Energy and American Institute of Architects, had well over 100 participants from scores of disciplines. About 15 to 30 people is best for holding the atmosphere of creative, collaborative, constructive tension captured in that African proverb: if you want to walk fast, walk alone. If you want to walk far, walk together. Often we kick off a charrette with this little cowboy video about how our facilitators will be helping us all to roam freely, learn rapidly and widely, and all end up in the unexpected place of discovery.
This man right here is my great-grandfather. He's the first cat herder in our family.
Herding cats. Don't let anybody tell you it's easy. Anybody can herd cattle. Holding together 10,000 half wild short hairs. Well, that's another thing altogether. Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning right here. And if you look at his face, it's just ripped to shreds, you know.
You see the movies, you hear the stories. I'm living a dream. Not everyone can do what we do.
I wouldn't do nothing else.
It ain't an easy job, but when you bring a herd into town and you ain't lost a one of them, ain't a feeling like in the world.
Yes, managing the complexities of new business.
Well, Charrettes follow culture. So for a Texas Instrument chip fab, our leader expressed similar ambitions in fluent Texan. He said, "We want big honking ideas," by which he meant, holy cow, over the top, no nonsense, knock you out. I don't know why I didn't do this before now, because it will save me a whole lot of money and time. And we ended up with 16 big honking ideas, 13 of which saved capital cost as well. We ended up with large savings in energy, water, and emissions at a 30% lower total capital cost. So that new chip fab was $230 million cheaper to build. That let it be built in Texas, not China, saving about 1,000 high-tech American jobs. Interestingly, when the semiconductor toolmaker Applied Materials and asked me to come to the main Chinese chip making conference and explain how we had done that, Texas Instruments wisely and bravely agreed. Said, this will be good for the whole industry. We'll compete on other stuff. It's kind of the same reason that Volvo shared its anti-lock braking technology with all its competitors, and Tesla is sharing its patents with all automakers. It's good for all of them and for everybody. Now, the rules of effective charrettes are simple. And they're kind of like the rules that we like to follow in our own puzzlers, which are a little sort of micro charrette. So maintain beginner's mind. Don't just copy what you already know. Be curious, learn from everybody. Be completely open to new ideas, lots of beginner's mind. Be open to errors. You know, if everything worked, we didn't take enough risk. And you start with brainstorming rules. No idea is a bad idea. Don't choose yet, just explore. Zoom out to wide angle initially. Later, we'll zoom back in to analysis and design. Don't worry if it feels a bit chaotic. If the process feels disorderly, that's perfect. Everything's going to come together naturally at the end. You know, there's, I remember once on the infectious hepatitis, I was visiting an Intel chip fab, and there was a pipe up above that made a precise right angle turn and then continued. I asked, what's that about? So, well, this is copied from another factory that had a structural pillar at that location. Wonder what happened to the pillar. That wasn't copying exactly. You know, I ran into a wonderful German engineer who said he had 30 years experience, and that means he spent a year making mistakes and 29 years repeating them. Comedian Dudley Moore added, I've learned from my mistakes. I'm sure I could repeat them exactly. So beginner's mind, as always, is the key. And this course doesn't actually use a charrette process, although we distill little bits of it into puzzlers, but it does guide you to extreme energy efficiency by helping you apply 8 simple methods, each of which has important benefits. You start with intent. Why are we doing this thing? You try to eliminate the task before you do it. You put demand before supply, downstream before upstream, application before equipment, people before hardware, passive before active, quality before quantity. And there are, of course, important benefits that flow from these and that will by now be familiar to you. They're not identical to our first lecture's 10 pillars, but that's okay. Our next lecture is going to make these 8 methods more concrete by applying them to actual industrial equipment. And then in our third industrial lecture, we'll zoom out to applying these learnings in actual plants and processes. Thank you. Hope you'll feel everything I've said is obvious. As Marshall McLuhan said, only puny secrets need protection. Big discoveries, he said, are protected by public incredulity.